Hi guys, welcome to this video. I'll be walking you through the third paper of OCR Physics A, which is the H556 Unified Physics in the exam series of 2024. So let's get started with the first question. In this question, we are given that a flute is a musical instrument made from a long tube that is open at both ends. A stationary sound wave in the tube produces a musical note, and the lowest frequency note that a standard flute produces in air is 262 Hz. So essentially, we are given the fundamental frequency F0. The speed of sound in air at temperature of 20 degrees is 340 meters per second. Show that a standard flute has an approximate length of 0.65 meters. So, firstly, we know that if you have two open ends, at the fundamental frequency, the wave would look something like this. This means that the length is equal to half a lambda. And so we can work out the value of this lambda given the frequency and the speed. Lambda is V over F, where it's 340 over 262, which gives me 1.297 something meters. And then from here, I can work out the length by dividing this number by 2. And that gives me 0.648 ... meters. So then in part B, we have been given an equation for the speed of sound, and we are also given that gamma is just a dimensionless constant that depends on the gas, R is the molar gas constant, T is the absolute temperature, M is the molar mass of the gas, along with some other values as well in the data table. Then for part I, it says the kinetic model of an ideal gas assumes that there are a large number of particles in rapid random motion. State two other assumptions for the kinetic model of a gas, of an ideal gas. You could say that the volume of the gas molecules is negligible compared to the volume occupied by the gas itself. And secondly, force exerted is negligible except during collisions. Part II. A standard flute is placed inside a sealed chamber, and the temperature of the chamber is minus 10 degrees Celsius. Calculate the lowest frequency that the flute could produce inside the chamber. Okay, we are looking at the above formula, and we know that right here that the temperature is absolute temperature, which is therefore in kelvins, and we've been given that the gamma value is 1.674 helium, and the molar mass is 4 grams per mole. We're going to use these values in the formula. So V is equal to 1.67 times 8.314 times by 273 minus 10, so 263 kelvins, divided by 4, converted into kilograms per mole, and then we simply square root that. So this gives me an answer of 955.5 meters per second. The value of lambda was 1.297. I can work out the frequency by using V over lambda, and that is going to give me an answer of 737 Hertz. Let's move on to the next question. Number 2, it says a group of students investigate the circuit shown in the figure below. there are n capacitors, and each capacitor has a capacitance of C connected in parallel, and there are n resistors, each with resistance R connected in series. So, in other words, the total capacitance is just N times C, and the total resistance is just N times R. Okay. Then it says initially the students close the switch X. They then note the reading on the ammeter. So they've closed the switch and they are measuring the current that's passing through the circuit. And the students then open the switch to record the time t for the reading to fall to half its initial value. And we've been given some data points along with the number of capacitors and resistors. In part A, it's not asking us to do anything for this table for now, so we'll just come back to it later. In part A, it says show that T equals ln 2 n squared RC. Okay, so we know that in terms of I is equal to I naught e to the minus t over RC. And we also know that I is half of I naught. Once you simply cancel out the I naughts, you're going to be left with half equals e to the minus t over RC. Take the ln of both sides and you would get ln of half equals minus t over RC. Ln of half is the same as minus ln 2. So that's going to be cancelling out the negative here. I should replace this with capital T because this is the time that they are specifically mentioning for the current to half. So there we go. T equals RC times ln 2. And because we know that there are total n number of resistors and n number of capacitors, if we introduce that over here, we'll have n times R and then n times C, same ln 2, which gives you n squared ln 2. In part B, it says the students write in their lab books, our data is precise. Evaluate this statement. Okay, for 2 marks. So if we go back up to this table, we realize that the range for the first set of values is 14.7 minus 14.1. So the range happens to be 0.6, which is fairly small. And if we look at some more data values, the next one, for instance, it's going to be 50.3 minus 49.6, which gives me a value of 0.7. So the answer is that, yes, they're right. The data is precise. Precision comes from the fact that the data collected should have a small spread. We can support our answer with these values. Part C. The results table is repeated below. We need to complete the mean values of the first 2 readings. Well, that's really simple. That's just going to be added all up together and divided by 3. So that will be 14.4 and 50.0. Then for part D, the student begin to plot a graph of t against n squared and complete the graph below and plot the 6 results from the table. You're not expected to include the error bars. So first of all, let's label our y-axis. I'm going to go up to 600, or rather just 500. So let's just do 100, 200, so on and so forth. And then we have t in seconds, and we're going to plot these points on the graph. For part II, we have to draw a straight line of best fit on the graph. Let's connect these points as closely as possible, like so. That will do. And then we have to calculate the gradient of the straight line of best fit. So I'm going to be a little cheeky and use the values from the table. The maximum value is 504.2 and the minimum is 14.4 for n equals obviously 6 squared and 1 squared. So the gradient shall be equal to 504.2 minus 14.4 divided by 36 minus 1, which gives me an answer of 13.99 or 14. So that is the answer here. Next part, calculate the value. The value of C is known to be 1000 microfarads plus or minus 5%. Use the gradient value from part to find a value of R in units of kilo ohms, including an absolute uncertainty. Okay, so we need to relate our gradient to the formula. Now we know that T is equal to n squared RC ln of 2, and we know that T over n squared is the gradient. So that means that R is equal to the gradient divided by the value of C times ln 2. So we know the gradient is 14 and the value of C is 1000 microfarads. So it will be just times by 10 to the minus 6, which leaves you with 10 to the minus 3, followed by ln 2. So that is going to be 20,205.74 ohms. To find the percentage uncertainty, we are going to do 5% of 20205.74, which gives me a value of 1010.28 ohms. The answer given in kilo ohms will be 20 plus or minus 1. Part E. Following the investigation, the student discovered that the sixth 1000 microfarad capacitor connected to the circuit was actually two of 470 microfarad capacitors connected in parallel. State the type of error caused by this mistake. Well, that will be systematic error. Systematic because it's going to lead to consistent mistake. And it is coming from a faulty or using the wrong equipment, using wrong capacitors. It says, explain the effect that this error would have. R would be smaller due to a shallower gradient as T is smaller, as the current discharged through two capacitors in parallel rather than just one, which was originally thought to be 1000 microfarads. In question number 3, we've been given that a scientist uses a rocket to study the Earth's atmosphere. And the rocket starts from rest at t equals 0 seconds. And let's highlight some words. And it accelerates due to the engine's thrust. And at t equals 50 seconds, the rocket fuel runs out and the engine stops. At point B, its velocity is 3.1 kilometers per second at an angle of 75 degrees to the horizontal. The rocket continues on a curved path to reach a maximum height, h, at point C. Now in the first part, it says the rocket engine works by expelling hot gas backwards. Explain using Newton's laws of motion how the engine causes the rocket to accelerate between t equals 0 to 50 seconds. As the engine exerts a backward force on the hot gases, the gases will then exert a forward force back on the rocket according to Newton's third law. And since the forward force is greater than the backward force and of course the weight of the rocket, the resultant force causes the rocket to accelerate. Part B. The rocket reaches its maximum height at point C. Estimate the vertical displacement h between point A and C, assuming gravity is 9.81 throughout. And then clearly state any other assumptions required at each stage in your calculations, and then followed by evaluating the assumption that g is 9.81 meters per second squared between A and C, supporting your discussion with a calculation, assuming that the radius of Earth is approximately 6,400 kilometers. Let's look back at the diagram to work out the vertical displacement h between A and C. So, as we know, h is the total vertical displacement, and firstly we should work out what is the displacement between A and B. Okay, so I'm going to call it S from A to B. And then we will work out what is the displacement from, for instance, from B to C. And I will call that out S, B to C. And then obviously H is the sum of the two, the vertical displacement basically. And so let's break this velocity down into its components. And I'm just interested in the vertical component of the velocity, which is going to be 3.1, so 3,100 meters per second times by sine of 75 degrees. Okay, and I'm going to use the time and this value to work out the value of S from A to B. Okay, so let's write this down over here. So from A to B, the displacement is going to be 3,100 sine 75 times by the time divided by 2, because it's the average velocity that we are considering, and we're using essentially S equals U plus V over 2 times by T formula here. So that would be 7.49 times 10 to the 4 meters. Righty. So that's done. Now let's go on back to the diagram and let's talk about B to C. It will have initial velocity at B, which will be 3,100 sine 75 degrees. Okay. And for point C, V will be 0. Okay. It doesn't have a vertical component. So that's mainly it. And we can set up our suvat to work out. So let's just put down from B to C in terms of suvat. U is 3,100 sine 75. V is 0. A is minus 9.81. We don't really know the time. So we can work out using V squared equals U squared plus 2AS and rearrange S as V squared minus U squared over 2a. So that will give me, of course, 0 squared minus 3100 sine 75 degrees squared divided by 2 times minus 9.81. And that gives me a value of 4.6 times 10 to the 5 meters. And now all I got to do is add the values. So h, therefore, is going to be 7.5 times 10 to the 4 plus 4.6 times 10 to the 5, which gives me approximately 5.4 times 10 to the 5 meters. We also need to talk about any assumptions made during each stage of our calculation. For instance, from A to B, we assumed that the acceleration was constant. And for part B to C, we assumed that the air resistance was negligible. So those will be the two assumptions made. And let's move on to the next one, where we have to evaluate the assumption that G equals 9.81 between A and C is truly accurate, given that the radius is 6,400 kilometers. For this, I'm going to use the formula G equals Gm over R squared, where G is inversely proportional to R squared. At point A, G, let's say A, is proportional to 1 over Ra squared, and at C, Gc is inversely proportional to Rc squared. So now if we compare these two, the given fact is that the Ra is on the surface and C is at a certain height, we can set up a ratio. So we can see that Gc over Ga is equal to Ra squared over Rc squared, which in turn then means I can just plug in the values. The radius of the Earth is 6,400 kilometers, and the height was 540 or 534. Originally, that's what I got as kilometers, and add that to 6,400 because it is from the center of the Earth. Square that, and I end up getting roughly about 0.85, which means that there is a 15% drop G. So that means that our assumption that it's consistent is incorrect. All right, so let's move on to the next part now. It says the length of an unloaded spring is approximately 4 centimeters. The force constant is 0.62 newtons per centimeters. Describe how you could determine K using an appropriate experiment. I think this is one of the easiest questions asked. So we can start by loading 1 Newton weights and measure the extension using a meter ruler each time. And we repeat our measurements to get an average. And then we draw a graph of force versus extension and then calculate the gradient of the straight line, as we know that K will be equal to F over X. The figure below shows a block of mass 0.2 kilos attached to one end of the spring. The other end of the spring is attached to a fixed support vertically above. In position P, the block rests in equilibrium, and the extension of the spring is 3.2 centimeters. In position Q, downward force F is applied, and so that it rests a distance d below its position at P, and the extension now is 8.5 centimeters. So given that the force F is now removed, calculate the magnitude of the block's initial acceleration at the instant that the force is removed. Assume that the spring is not extended beyond its limit of proportionality. So let's just look back at the diagram. Now we are told that this force over here is removed. So the spring is going to go in that direction. The acceleration will be in that direction. Resultant force will be in that direction. So we also know that there is extension or compression in this case. Okay, so we know, first of all, that there is resultant force acting in this direction. And there's also F equals kx. Bear in mind that you have to work out the extension. The extension is going to be 8.5 minus 3.2 centimeters, and that will give me 5.3 centimeters. And we don't have to convert this into meters because the value of k is given to us in newtons per centimeters. So that's 0.62. So let's write these couple of things down. So first of all, we know that the forward force or the downward force is 0. And we know that the other force is kx. And that is equal to the resultant force, which is ma. So it will be equal to k times x over m, where k is 0.62 times 5.3 over the mass, which is given to us as 0.2. So that is going to give me a value of 16.43, or I can just say 16 meters per second squared. Okay, part II, it says the block now moves with simple harmonic motion. Calculate the frequency of this motion. We know acceleration is minus omega squared x. And we also know that omega is 2 pi f squared times x. And we can cancel out the negatives because we knew that the acceleration over there on the other side is negative. So we can say that we have f as 1 over 2 pi square root of the acceleration, which is 16, divided by the extension, which is x. So it will be 16 over, make sure you convert this into meters, 5.3 times 10 to the minus 2, and then times pi, 1 over 2 pi square rooted. Right there. Frequency turns out to be 2.8 hertz, and that's the answer. Let's move on to part C, where it says the block is replaced by a strong magnet L and of slightly greater mass. The oscillation frequency of this new arrangement is 2.5 hertz. The magnet L is placed inside a coil X of an insulated copper wire. This coil X is connected with long wires to a second identical coil Y. The second strong magnet M is placed inside Y and attached to a vibration generator. The vibration generator is then forced to oscillate with a frequency of approximately 2.5 hertz by adjusting the signal generator. As magnet M oscillates, it moves in and out of coil Y. The magnet L also begins to oscillate. Explain why L oscillates. As M oscillates, there is an alternating potential difference produced in the coil Y due to the change in magnetic flux linkage. And as a result of this, an alternating current flows through X, which then causes L to oscillate due to alternating force exerted on it. Remember that the coil X and magnet L's magnetic fields are interacting. In part II, it says the frequency of the vibration generator is now varied between 0.5 to 5 Hz. Suggest how the amplitude and the frequency of the oscillations of L will change as the frequency is now varied. It would resonate at 2.5 Hz because the oscillation frequency is 2.5 Hz and the vibration generator is also vibrating at 2.5 Hz. So it will reach the maximum amplitude. So here's my diagram. We have our amplitude on the y-axis and frequency on the x-axis. As the frequency increases from 0.5 Hz to 5 Hz, it will reach a maximum amplitude at 2.5 Hz. So let's say this value is 0.5 Hz, and then it would go down following that. So that is beyond. So perhaps this is going to be 5 here. We can't quite tell, but I'll just leave it there. And we know it's maximum because resonance occurs here as the forced frequency is equal to the natural frequency. So those are the couple of things I would mention, but I think everyone is very aware of this diagram being quite self-explanatory. When the frequency of the vibration generator reaches or meets the oscillation frequency or natural frequency, it would resonate at 2.5 Hz, that is, and the amplitude will be maximum at resonance. Let's move on to the next part. Question number 5, we have to explain what is meant by internal resistance of a cell. It's simply the lost volts per unit current. And II, the EMF of a cell. Well, it's the work done on charges as they pass through the source. Part B. A cell has internal resistance R, which is 1.2 ohms, and an EMF of 5.6 volts. When the cell is connected to a filament lamp B, the current is I. And here we have an IV characteristic for B as shown in this diagram. And we have to determine the current in the circuit. This is quite an interesting question. Let's just look back at the diagram and the graph, and then we can work this out slowly and carefully. We know that this is 5.6 volts and 1.2 ohms. We've been given the current passing through the bulb as the voltage is varied. Okay, so that is not the same as the current going through the circuit. We have to think about this in a slightly different fashion where let's just start with EMF equation being V plus I times R. Now we know that I is therefore EMF minus V over R, or simply EMF over R minus V over R. I is equal to 5.6 divided by 1.2 minus 1 over 1.2 times V. What does that tell us? That can give us the value of the y-intercept, which is 4.7, minus the value of our gradient, which is 0.83. And according to this equation, it will have a y-intercept of 4.7, so that's roughly here. And I don't know where it would cross the x-axis, so let's find that out when current is 0. So that will be 0 equals 4.7 minus 0.83 V. So this means that V is 4.7 over 0.83, and that gives me a value of 5.66 or 5.7 volts. So 5.7 volts will be around about here. If I just join these 2 points, that will be my straight line. The intersection of these 2 graphs is going to give me the answer. So if I just read that off, it gives me anything between 2.8 to 3 amps. So I'll just say 2.9 amps will be my answer. This was more mathematical than anything else, and I think this is one of the hardest questions I've seen. So I don't know how many students would have gotten this right. The IV characteristic curve for B did not quite represent the current passing through the circuit, as the current varies in the bulb. Watch out. Hopefully they will come up with questions like this so we are able to practice them, but this was quite harsh, I believe. Let's move on to our next part, question 5, part C. In this question, a student wants to determine the internal resistance R and the EMF of a different cell. The student knows the internal resistance is approximately 0.1 ohms. And the only other electrical equipment available is voltmeter, ammeter, a sensitive thermistor, known to have a resistance of approximately 0.1 ohms at 20 degrees, several connecting wire crocodile clips, and then we have to describe how the student can determine R and EMF for the cell, include collection and analysis of the data, and determine the uncertainty in the values of R and EMF. Okay, so this one is rather easy. EMF is equal to V plus I times R. Graph of that temperature and resistance will vary. And so let's start by drawing a circuit. We will have our cell, an internal resistor, followed by an ammeter, a thermistor, then we will have a voltmeter across this thermistor. Number 1, we would record the voltage before increasing the temperature. We would increase the temperature by using a water bath each time by 2 degrees Celsius, for instance, from 0 degrees. And we would use a thermometer to measure the temperature. Then we would record the values of voltage and current through voltmeter and ammeter respectively, and then we would repeat these readings 3 times to get an average and plot a graph of V versus I. Okay, then in terms of the analysis of the results, we know that V is EMF minus I times R. So now if we compare this with the equation of straight line, which is y equals, well, C plus mx, then m will be negative R, or internal resistance, and C will be the y-intercept. Okay, and then finally, in terms of uncertainty, I'd say obtain a range of values of V and I each time. Calculate the absolute uncertainty by doing half of the range and then plot the error bars to obtain a line of worst fit, and then we can work out the gradient, and then that would help us work out the uncertainty in the internal resistance. And then for the uncertainty in the EMF, which is the y-intercept, we would look into the steepest and the shallowest lines, and then we are just going to half the y-intercepts of those two, take away the difference, and then half it. The figure below shows the path of a proton moving in a region occupied by both electric and magnetic fields. The direction of the electric field is perpendicular to the direction of the magnetic field lines, and we've been given the 2 directions like so. So the magnetic field is basically out of the plane of paper, out of the plane. And the uniform electric field is directed upwards, and this is the strength of the electric field, and the uniform magnetic field is directed with a magnetic flux density of this many Teslas. At point X, the proton is moving horizontally to the right. The magnitude of the magnetic force is given to us. Similarly, at point Y, this proton is moving vertically down, and we have been given the magnetic force. The electric forces acting on the proton at X and Y are not shown in the diagram, and we need to show that the magnitude of the constant electric force acting on the proton is about 10 to the minus 19 newtons. The electric field is directed upwards, so this proton being positively charged will have an electric force like, and same here, it's constant. So I'm just gonna work out the magnitude of this electric force by using the electric field strength and the charge on the proton. So 0.9 times by 1.6 times 10 to the minus 19, and that will give me 1.44 times 10 to the minus 19 newtons, which is about the same magnitude order. Part B, suggest why the magnetic force acting on the proton has different magnitude at X than at Y. At X, it's following a circular path. At Y, it's not following a circular path. We know that F equals BQV, and since it's a circular path, its velocity is constantly changing. Part II, at X, the motion of the proton is instantaneously equivalent to that in a circle at constant speed. Calculate the radius of the circular motion. So first of all, we know that because it's circular motion, there will be resultant force, and that would be mv squared over r. And we can work out r by, of course, rearranging, but we need velocity, first of all, and we also need to work out the resultant force. I would work out the velocity by using BQV, okay, and I'm talking about the magnetic force over here, so I'll just label it as FM. So V is therefore FM over BQ. Okay, so I'll use that later. And then secondly, resultant force. Let's go back up and look at point X. We know that the two forces, the magnetic force and the electric force, are acting in opposite directions. So I can work out the value of this by simply taking them away from each other. So 5.6 times 10 to the minus 19 minus the value that I worked out, which was 1.44 times 10 to the minus 19 newtons, and that would be my resultant force, followed by m v squared over bq squared, whole squared. And then once I put in all the values of m, let's just actually write this down. R is going to be equal to 1.673 times 10 to the minus 27, which is the mass of the proton, multiplied by 5.6 times 10 to the minus 19 squared, which is the magnetic force, divided by the answer over here, the difference between, which is 4.2 times 10 to the minus 19 newtons, multiplied by the square of the magnetic flux density, which is 5 times 10 to the minus 5, multiplied by the charge on the proton, and all squared like so, and that gives me 19.5, or rather 20 meters of radius. Okay, that was a good one. Now let's move on to our second part, where we have to calculate the magnitude of the resultant force acting on the proton at y. So let's check that out. So that's again relatively simple because it's forming a right angle triangle and the hypotenuse is going to be the resultant force. So let's write that down over here. So resultant force will be the square root of Fm squared and Fe squared. And we know the values, and we would end up with a value of 4.1 times 10 to the minus 19 newtons of force. Last part of the question, explain why the motion of the proton at y is not instantaneously equivalent to the motion in a circle at a constant speed. We know that from above, the proton is moving downwards at point y, and the resultant force clearly over here is not acting towards the center of the circle. There is no circular path, so it's not going to have a constant speed. Work is being done on the proton constantly to make it move and to change its speed. Therefore, it's not going to have constant speed. Remember, I'm not using the word velocity here. We're talking about speed, which means the magnitude. So I hope that makes sense. And that's the end of the paper. I hope you found this paper useful. There were good questions and not so good questions, but I guess that's how the third paper always is. So I will see you guys next time in my next video, and I'll be looking at the set 2 papers now, as requested by some of you. See you then.